Hi, this is Sudeep and I welcome you back to this wonderful journey of learning structure analysis with StatPro. If you are new to this channel, welcome. Please do hit the subscribe button to join us in this wonderful journey. And do press the bell icon for more notifications from the Structural Insider channel. Now in the last session, we have discussed about many possible centroidal axes of a particular cross section. And the question was, which of the centroidal axes is important to us? Well, we will choose a centroidal axis that would maximize the utilization of the material. Now we have to pay for every kg of steel or every cubic meter of concrete. So the cost is very important. So we would like to minimize this cost while ensuring the safety at the same time. So it's very important that we consider this material utilization. Now, if we actually have the maximum possible moment of inertia for bending, then it would lead to the minimum cost requirements or the maximum utilization of the material. So, what is the relationship between the maximum moment of inertia and the maximum utilization of the material? Well, the relation would become obvious when we discuss about the flexure theory. But for now, let us assume or consider that if we have the maximum moment of inertia for bending, or if we choose the bending to happen about the maximum moment of inertia, then the material utilization would be maximum. In the last session, we had derived the moment of inertias and the product of inertia about this axis y dash and z dash, where we had known the values of the moment of inertias and the product of inertias about the y and the z axis. That is, if we had known the values for the y and the z axis, that is, if we had known the values of Iz, Iy and Iyz, which is the moment of inertia about the z axis, which is this, the moment of inertia about the y axis, and the product of inertia about the yz axis. If we had known those values, we had gone on to derive the values of Iz dash, which is the moment of inertia about the z dash axis, Iy dash, which is the moment of inertia about the y dash axis, and which is Iy dash z dash, which is the product of inertia about y dash z dash axis. Now, and what is the value that we had calculated, or what is the value that we have derived? So Iz dash, if we know the values of Iz, Iy and Iyz, is given by this equation. If theta is the angle of inclination about of the y dash z dash axis from the yz axis, then Iz dash would be given by Iz plus Iy by 2 plus Iz minus Iy by 2 cos 2 theta plus Iyz sin 2 theta. In the same way, we had calculated the value of Iy dash as Iz plus Iy by 2 minus Iz minus Iy by 2 cos 2 theta and minus Iyz sin 2 theta. So this is the expression of Iy dash. And what would be the expression of the product of inertia about the y dash z axis? It would be given by this value minus Iz minus Iy by 2 sine 2 theta plus Iyz cos 2 theta. Okay, and if you want to see the details of this derivation, you can click on the link that is appearing on the screen above right now to go to that session where we had derived these expressions in details. Alright, now our question is to find out the maximum value of the moment of inertia. Now in this case, we are assuming that Iz is greater than Iy, right? And we intend to find out the value of the axis, or rather we intend to find out the z dash axis about which the value of the moment of inertia would be maximum. Now, just as a reminder, you can have infinite possibilities of the yz dash z dash axis between theta equal to 0 degree to theta equal to 360 degree. We had discussed this before. So, how do we then find out at which angle of theta we get a z dash that would give the maximum moment of inertia? Well, the problem is made simple by the maximum minimal principle of differential calculus. So what we need to do to calculate the maximum value of Iz dash is we will do a differentiation with respect to theta of the value of Iz dash. So Iz dash now is given by this particular expression here, right? So what we need to do then is it would be d by d theta Iz plus Iy by 2 plus d by d theta Iz minus Iy by 2 cos 2 theta, and then we have d by d theta of this term, which is Iyz sine 2 theta. Now, one of the things to notice here is that Iz, Iy and Iyz are the known values of moment of inertia about the y and z axis. So these are constant terms. So then the differentiation of this is a constant term. So the differentiation of the first term would be 0. The differentiation of the second term, so this would be a constant term. So that would come out. So it would be Iz minus Iy by 2 and differentiation of cos 2 theta. Iyz would be again a constant here. So Iyz, and then we have d d theta of sine 2 theta. Now we go on to differentiate, so it would become Iz minus Iy by 2. What would be the differentiation of cos 2 theta with respect to theta? It would be minus 2 sine 2 theta. And what would be the differentiation of sine 2 theta with respect to theta? It will be 2 cos 2 theta. So 2 cos 2 theta. So then it gives us, so this 2 and 2 would cancel off. So this would give us the value of Iz minus Iy sine 2 theta plus Iyz, it would give us the value of 2 Iyz cos 2 theta. Now, to give us the maximum value of Iz dash, diz dash by d theta has to be 0, right? So this has to be 0. Now what's the expression of, so we just sort of write this here. We just rub out these terms. So we write the final expression here. So this is Iz minus Iy sine 2 theta plus 2 Iyz cos 2 theta. So now for Iz dash to be maximum, this expression should be 0, which would mean that this expression should be 0. That is, and if we divide both sides of this equation by cos 2 theta, we would get, so Iz minus Iy sine 2 theta by cos 2 theta would give us tan of 2 theta, and this would be 2 of Iyz. Cos 2 theta by cos 2 theta would cancel off. This would be equal to 0. So we will have tan 2 theta as minus 2 Iyz by Iz minus Iy. So we can even express that as Iyz by Iz minus Iy by 2. So this means that we now know the angle at which Iz dash would be a maximum or minimum. Now Iz dash, since Iz is greater than Iy, we have assumed, so this is going to be the maximum. Now that would mean that at this particular angle, so at theta, at a value of theta where, so at this value of theta where tan of 2 theta is equal to Iyz by Iz minus Iy by 2, this is the value where the Iz dash would be the maximum. Okay, so this means that we can find out 2 theta from this expression. Now there is, so what about the root of this equation? Now 2 theta would have 2 roots 180 degree apart. And how do I know that? Okay, for that let me draw so let me draw this particular quadrant here. And we know that we will get a value. So tan is positive, the tangent of an angle would be positive if the angle lies either in this quadrant or this quadrant. So if the angles lies diametrically opposite, then we would get this value here. So that would mean that, see, if we actually draw a line like this, such that this represents the value of IYZ. So remember, in a right angle triangle, tan theta would be perpendicular by base. So we take this as the perpendicular of this right angle triangle here, where this one is the value of theta where this expression is satisfied. Say we have 2 theta dash, okay, 2 theta dash, and then the base of this would be IZ minus IY by 2. So in the same manner, in this case here, if we actually think about this right angle triangle, then this right angle triangle is located at an angle of, say, 2 theta double dash. And 2 theta double dash, this angle is nothing but 2 theta dash, right? So 2 theta double dash is nothing but 2 theta dash, which is this particular angle, plus 180 degrees, right? So plus of 180 degrees. So we can see that the solution of this particular equation would be located at 180. The roots of this particular equation would be spaced at 180 degrees apart, or that would mean that the angle theta would be spaced 90 degrees apart, right? So in this case, you again see that this value would be then minus IYZ, right? And this value would be minus IZ minus IY by 2, right? So minus and minus would give positive, and both would give the tan 2 theta as this value. So, both of this would satisfy this particular equation. So this proves that the 2 theta would be spaced 180 degrees apart, right? The solution of this 2 theta would be spaced, solution of 2 theta would be spaced 180 degrees apart. So we are saying that one of the solution is 2 theta dash and the other solution is 2 theta double dash. So if 2 theta dash and 2 theta double dash is spaced, the space between them is 180 degrees, then theta dash and theta double dash are spaced 90 degrees apart. So this would mean that there are 2 principal axes. What does it mean? You get 2 angles, right? You get 2 angles where this equation is satisfied. So this means 2 conclusions. There are 2 principal axes, and the other conclusion is they are spaced 90 degrees apart. So we reach these 2 conclusions. Okay, now let us do this. We retain this particular equation. Now we know that the solution of this particular equation is spaced, so theta, the solution of theta would be spaced 90 degrees apart. Okay, keeping that, we just remove the other part of what we have derived and we retain these expressions here on the board. Okay, now let us assume I dash y dash z dash as 0. Okay, about any theta, let us consider a value of theta such that this value is 0. Okay, so what does that mean? This would mean that this expression here, so iz minus iy by 2 sine of 2 theta plus iyz cos of 2 theta would be equal to 0. So that would mean that if you see what does it mean, then you would see that we would come to this conclusion that tan 2 theta would be iyz by iz minus iy by 2. And these two expressions are exactly the same. So what does this mean? Now this solution is supposed to indicate the principal axis. And this solution is supposed to indicate that the angles where the axis which is located at the angles given by this solution where the product of inertia is 0. So what do we conclude from this? We conclude that the product of inertia of the principal axis will be 0. So that's our third conclusion from this. So the first conclusion is that the principal axis are located at an angle 90 degrees apart. Okay, so there are two axes of where you have principal axis and they are located 90 degrees apart, and we have the product of inertia about those axes vanish. So this is the third conclusion. Okay. So now let us think about this. So let us redraw this diagram again of the four quadrants of locating the principal axis, and let us say that the first value of principal axis is located at an angle of 2 theta dash, and let the other principal axis be located at an angle of 2 theta double dash. So as we said that this value would be iyz and this value would be iz minus iy by 2. Similarly, in this case, this value would be minus iyz and this value would be minus of iz minus iy by 2. Now, let us now then consider that the value of, so if this is the value of tan 2 theta, what is 2 theta dash and 2 theta double dash? They are the solution from this particular equation. Okay, just let us be clear on this. So the solutions that for 2 theta are 2 theta dash and 2 theta double dash, and they are spaced at 180 degrees apart from each other. So they are spaced at 180 degree apart from each other. Okay, now what would be the value of sine 2 theta dash? Okay, now see, in this right angle triangle, this is the perpendicular, this is the base, so this is the hypotenuse, right? So now for sine 2 theta dash, that would mean that sine theta is what? Sine 2 theta dash would be what? Perpendicular by hypotenuse. So perpendicular is iyz and the hypotenuse would be given by square root of iz minus iy by 2 whole square plus of iyz square. So this is the value of sine 2 theta dash. And what would be the value of cos 2 theta dash, it would be base by hypotenuse, right? Cos 2 theta dash is base by the hypotenuse. So it would be Iz minus Iy by 2, and this would be the hypotenuse again. Right, so these are the values of sine 2 theta dash and cos 2 theta dash. Now, if we substitute 2 theta as 2 theta dash, we will get the major principal axis I1, or the moment of inertia about the major principal axis, which we can represent that as I1. Right, so now let me rub off this diagram. We intended to derive this figure out of this. So, we intended to derive these equations out of this figure. Now we can remove this. Now we will derive the value of the moment of inertia about the major principal axis and the moment of inertia about the minor principal axis. Now we have to, so let us do off with this particular equation now. So we will rub these values off. And we will use these values in this particular equation. Now, so remember the Iz dash is the maximum. So that's the moment of inertia for the major principal axis, which we would represent by I1, and the angle for where we would get this value is 2 theta dash. So we replace 2 theta with 2 theta dash. So we will write this as Iz plus Iy by 2 from this equation, plus Iz minus Iy by 2. So cos 2 theta dash would be given by this expression here. So it would be Iz minus Iy by 2 and into 1 by square root of Iz minus Iy by 2 whole square plus Iyz whole square, 1 by. So, and what about this last term? Well, this last term, remember, it's a major principal axis, it's a principal axis, so the product of inertia, or rather, sorry, this would remain. I'm so sorry. So this would remain. So then it would be plus Iyz into sine 2 theta would be given by Iyz by square root of Iz minus Iy by 2 whole square plus Iyz whole square, Iyz square. So then we can write these expressions. We'll rub off this figure, so we have to make space on the board so that we can. So I hope you can manage without this figure now. This should have been printed in your brains by now. So let us write this down so that we don't forget the expressions. So it is given by square root of and we have So these are the values of the sine of those angles. Now let us continue our derivation of this. So we get this as, if you continue, then it becomes as Iz plus Iy by 2 plus, then we have Iz minus Iy by 2 whole square into 1 by square root of Iz minus Iy by 2 whole square plus Iyz square. And then we have Iyz square. We have Iyz square into this value. So then we rewrite this expression as, we remove this, and we rewrite this expression, sorry, so we rewrite this expression as Iz plus Iy by 2. Then we have this value as 1 by square root of Iz minus Iy by 2 whole square plus Iyz square multiplied by, and remember what would be the values here? It would be Iz minus Iy by 2 whole square plus Iyz square. So then this would give a square root on the top, so the expression becomes the expression for the major moment of inertia becomes so this is the expression for the major moment of inertia. Similarly, you can find out the value of the moment of inertia about the minor principal axis by either substituting the value of 2 theta dash in this particular equation directly, or remember we found out two roots, the other was 2 theta double dash, or instead you could put the value of 2 theta double dash in this particular equation to find out the value of the moment of inertia of about the minor principal axis. Let me give you the expression. It would be the same type of expression, so I am not going to do that again. It would be given by Iz plus Iy by 2 minus square root of Iz minus Iy by 2 whole square plus Iyz square. So the major moment of inertia, assuming that Iz is greater than Iy, we will get this value for the major principal axis, the moment of inertia about the major principal axis, and this value for the moment of inertia about the minor principal axis. So in other words, I can write Imax for the moment of inertia about the major principal axis, and I mean for the moment of inertia about the minor principal axis as And we can express that both of major and minor, or maximum or minimum, in one equation like this. IYZ square. And this is the value of square. So I hope this gives you a clear explanation of the expressions, how the expressions of calculating the moment of inertia, the major moment of inertia and the minor moment of inertia of a section. And I have given you the full expression as to how you can do that. So you might have been surprised by my subtle mention of the term principal axis while I was doing the deduction. So I thought that that would need a bit of explanation. So we started our exploration. To find out an axis about which the moment of inertia would be maximum. And now that we have solved the equation, we saw that we have actually identified an axis which I am drawing in red, where the moment of inertia would be maximum, and that is located at an angle theta dash from an axis system about which we know the values of Iy, Iz and Iyz. Now this theta dash would mean that here is a theta dash angle as well, and this would be the direction of that axis. And let us call that axis as 1. I'll tell you why. So let us call that axis as 1. Now what we have said is that there is another axis. When we look into that equation which locates the axis about which the moment of inertia is maximum, it gives two values. So the other value is located at 90 degrees from 90 degrees apart. So then if this is theta dash plus 90 degree would give you this angle that is perpendicular to this line, and let us call this axis as 2. Now what does it mean? Now does it mean that the moment of inertia about both axis 1 and 2 is the maximum? Now to answer this question, let us go back to the principle that we had solved in the earlier session. For details you can click on the link that is appearing in the screen above, and where we have proved that if we know the moment of inertia about an axis system, say y and z, and then we find out the moment of inertia about other axis system y dash z dash, then iy plus iz will be equal to iy dash plus iz dash, right? So in this case if the moment of inertia about the axis 1 is maximum, right, then so if we have iy plus iz and we have the maximum moment of inertia about axis 1, then it can never be that we would have another maximum another axis which would have a maximum moment of inertia. So then this would mean that the moment of inertia about this axis 2 would actually be the minimum, right? So the two roots of that equation which locates the principal axis, one would identify the axis about which the moment of inertia is maximum, and it would locate another axis 90 degree apart. So like this angle here is 90 degree. So this angle here is 90 degree. So 90 degree apart. would actually locate an axis where the moment of inertia would be minimum. Now, this axis 1, where the moment of inertia is maximum, would be called moment of inertia is maximum, is called the major principal axis. So what is principal axis? A principal axis is an axis where the moment of inertia can either be maximum or minimum. Now, where that principal axis about which the moment of inertia is maximum is called the major principal axis, and that principal axis where moment of inertia is minimum is called the minor principal axis. Okay, so I hope that now it will remove the confusion that might have arisen when I mentioned the principal axis while I was writing that conclusion. So what was the conclusion? The conclusion was that there are two principal axes, and now we know that what is the principal axis. Now, principal axis is where the moment of inertia of the section is either maximum or the minimum. The major principal axis is where the moment of inertia is maximum, and the minor principal axis is where the moment of inertia is minimum. And the major and the minor principal axis are given by angles that are spaced at 90 degrees apart. So what are the conclusions from this particular session? Well, the conclusions of this particular session are that the maximum and minimum moment of inertias are on axes that are located 90 degrees apart from each other. 90 degrees apart. Number 2 is that the maximum moment of inertia is called the major principal axis. So these axes, so I should say that the maximum the minimum moment of inertias are on axes that are located at 90 degrees apart. Now, those axes, it would be plural, so axes, those axes are called the principal axis. Principal axis with the maximum moment of inertia with max moment of inertia is called major principal axis, and principal axis with minimum moment of inertia, principal axis with minimum moment of inertia is called minor principal axis. And finally, the product of inertia vanishes about the principal axis. And we have also found out the values of the major and minor, the principal moment of inertias from the values that we knew about an axis system YZ. So now we have the answer to our question. The set of centroidal axes that we were looking for to have the bending happen was the principal axis system. And we now also know that if we know the moment of inertias about any set of centroidal axes, we can locate the principal axis system. I hope I have been able to add some value today, and if I have, if you think I have, please to hit the like button so that this content reaches out to many more who would be looking for such contents. I hope to see you in my next session. Till then,